We will now discuss the solution of a problem from the section Algebra, and in the Algebra there is a subsection called Number Theory. The problem is on Number Theory from the section Algebra. The problem is on the concepts of primitive roots modulo a given prime number 17. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the part C. The given question is a positive integer n which is co-prime to 17 is called a primitive root modulo 17 if n power k minus 1 is not divisible by 17 for all k with 1 less than or equal to k less than 16. Let a, b be distinct positive integers between 1 and 16. Which of the following statements are true? We are given four options. Option 1. 2 is a primitive root modulo 17. Option 2. If A is a primitive root modulo 17, then A square is not necessarily a primitive root modulo 17. Option 3. If AB are primitive roots modulo 17, then the product AB is a primitive root modulo 17. Option 4. Product of primitive roots modulo 17 between 1 and 16 is congruent to 1 modulo 17. We are given a definition. The definition reads as a positive integer n which is relatively prime to 17 is called primitive root modulo 17 if n power k minus 1 is not divisible by 17 for all k with 1 less than or equal to k less than 16, that is k is equal to 1, 2, 3, 4, 5 up to 15. Let a comma b be distinct positive integers between 1 and 16. Then we have to discuss the validity of the following four statements given in the options 1 to 4. Now, before getting into the problem and the discussion about its solution, we review some results on primitive roots modulo n. First, fix a natural number n. Consider Zn plus n cross n. This is the ring of integers under addition modulo n plus n and multiplication modulo n cross n. Now, we have studied in ring theory the units of this ring or any ring forms a group under multiplication. The group of units of Zn we consider now, call it as U of n. U bracket n is equal to the set of all x belongs to Zn which are relatively prime to n, that is the GCD of x and n is 1. Un consists of the units. You see, an x which is relatively prime to n is invertible under multiplication, and such an element is called unit. So Un consists of units, and this forms an abelian group of units of Zn under multiplication modulo n. And this is a very well known group in our group theory. And we know the order of un is phi of n, where phi is Euler's phi function. What is primitive root modulo n? Let a belongs to n, the least positive integer m, such that a power m is congruent to 1 mod n is called the order of a modulo n, denoted by order of a modulo n. Order suffix n bracket a is to be read as order of a modulo n. And this is the usual order of an element in group theory, but we are talking in terms of the modulus of n, the order of a modulo n. And you know, the order of an element always divides the order of the group. The group is un, so therefore the order of a modulo n divides order of un. The order of un is phi of n, where phi is the Euler's phi function. If order of an element a modulo n is equal to the order of the group un, that is equal to phi of n, then a is said to be primitive root modulo n. That means a belongs to un, and if the order of a modulo n is equal to the order of the group u of n is equal to phi of n, then a is said to be a primitive root modulo n. So, cyclic group and the number of generators. Let a belongs to u bracket n be a primitive root modulo n. That means the order of a modulo n is phi of n. Then a will generate u of n. So, a generates u of n. That means un becomes a cyclic group generated by this a, where a is the primitive root modulo n. That means every primitive root modulo n will generate u of n, and it will be a cyclic group and generated by a. And now, when it is a cyclic group, now how many generators are there for u of n? So, u of n has precisely phi of the order of u of n. That means phi of n generators. Agreed? Because u of n is order phi of n. So, the number of generators will be phi of the order of u of n, that is phi of n generators are there. Now, this much of information that is sufficient for us to discuss the solution of the given problem. Now if a is a generator of un, now which powers of a will also be a generator? That means, in other words, we say if a is a primitive root modulo n, when a power k is also a primitive root modulo n, that's what we are asking. So, a power k is a primitive root modulo n if and only if the GCD of k comma phi of n is equal to 1. That means k is relatively prime to phi of n. Then a power k is a generator, is a concept of a generator, and it's also primitive. So, a power k is a primitive root modulo n if and only if the k and phi of n are relatively prime. So, we are ready now. Let's get into the problem for the discussion of the solution. We have n belongs to n. N is a natural number. N is co-prime to 17. That means the GCD of n with 17 is 1. So, n comma 17 is 1 means n is a unit. Therefore, n belongs to U17. Now, U17 consists of all those numbers which are relatively prime to 17. 17 being a prime, the elements are 1, 2, 3 up to 16. The elements of U of 17 is the set of all 1, 2, 3, 16. And n is, we are given a definition. The definition reads as, n is a primitive root modulo 17 if and only if n power k minus 1 is not divisible by 17 for all k with 1 less than or equal to k less than n. Less than n. This is same as if and only if n power k is not congruent to 1 modulo 17. N power k is not congruent to 1 is same as n power k minus 1 is not divisible by 17 for all k with 1 less than or equal to k less than 16. It is same as if and only if the order of n modulo 17 is equal to order of U17, that is equal to phi of 17. Phi of 17 is 16. Phi of p is equal to p minus 1. 17 is a prime, therefore phi of 17 is 17 minus 1, that is 16. Now let's discuss the validity of the statement that is given in the primitive in the option 1. So the option 1 is 2 is a primitive root modulo 17. Is it so? Now 2 comma 17 is 1, right? Because the GCD of 2 and 17 is 1. Therefore 2 is a unit. Therefore 2 belongs to U17. 2 belongs to U17. Note that for k is equal to 8, 2 power k, that is 2 power 8. 2 power 8 is 2 power 4 into 2 power 4, 16 into 16, that is 256. And 256, when you divide by 17, you will get the remainder 1. So 256 is congruent to 1 mod 17 because 17 multiplied by 15 is equal to 255. That means when you divide 256 by 17, the remainder is 1. So 2 power 8 is congruent to 1 mod 17. 1 mod 17. That means for a k is equal to 8, it's congruent to 1. So but is not congruent to 1, then it will become primitive root. It is congruent to 1. So by definition, this is the order of 2 modulo 17 is 8. But this order is 8 is not equal to 16, that is phi of 17, it is not equal to. It's not equal to. When the order of 2 modulo 17 is not 16, then 2 is not a primitive root modulo 17. Therefore, the option 1 is not true. Now we ask a question and claim that 3 is a primitive root modulo 17. This we will see in the next slide. We have a table here. First column k, second column 3 power k is congruent to R mod 17. We will see for k is equal to 1 to 15, 3 power k, is it congruent to 1 mod 17 or not congruent to 1 mod 17? For k is equal to 1 to 15, 3 power k is not congruent to 1 mod 17, then 3 will qualify to be a primitive root modulo 17. Let us take k is equal to 1. 3 power 1 is 3 and it is 3 modulo 17 because less than 17. 3 is. Now k is equal to 2. 3 square. Multiply the remainder here by 3. 3 3s are 9, which is less than 17. Is still is congruent to 9 modulo 17. K is 3. 3 cube. 3 nines are 27. 27 modulo 17 is 10. Agreed. 3 power 4. 3 tens are 30. 30 minus 17, 13. So congruent to 13 mod 17. K is equal to 5. 3 13s are 39 minus 34 is 5. So it's congruent to 5 mod 17. K is equal to 6. Multiply this 5 by 3. 3 5s are 15, which is less than 17. Therefore, congruent to 15 mod 17. K is equal to 7. 3 15s are 45. Minus 34, 11. So 3 power 7 is congruent to 11 mod 17. K is 8. 3 power 8. 3 11s are 33. Minus 17, that is 16. 16 is minus 1 modulo 17. Agreed. 9. That is 3 minus 1 multiplied by 3. Minus 3 modulo 17 is 14. 10. K is equal to 10. 3 power 10. 3 14s are 3 into minus 3. Minus 9. Minus 9 is modulo 17 is 8. 11. 3 power 11. 3 8s are 24. Minus 17. 7 congruent to 7 modulo 17. So like that 12, 13, 14, 15 we have done. In all these things, what are we observing? We observe that 3 power k is not congruent to 1 mod 17 for all values of k 1 less than or equal to k less than 16. This is by definition 3 is a primitive root modulo 17. You further see 3 power 15 is congruent to 6 mod 17. 3 power 16, 3 power 15 is congruent to 6 mod 17. Multiply by 3. 3 power 16 is congruent to 3 6s are 18. 18 modulo 17 is 1. So 3 power 16 is congruent to 1 mod 17. That's also the other definition of the primitive root modulo 17. Thus 3 is a primitive root modulo 17. Now we are ready to discuss the other options. 3 belongs to U17 because 3 is relatively prime to 17. 3 is co-prime to 17. Therefore, 3 belongs to U17. And 3 is a primitive root modulo 17. That's what we have seen in the last slide. Right? Now, if 3 is a primitive root, then 3 generates U17. So U17 is generated by 3. Therefore, U17 is a cyclic group generated by 3. Now, we can count the number of generators of this cyclic group U17. The number of generators are phi of 17. That is equal to phi 17 is 16. That is phi of 16 is 2 to the power of 4. That is equal to, use the Euler's phi function formula, 2 to the power of 4 into 1 minus 1 by 2. When you simplify, you will get 8. So there are 8 generators for U17 and 3 one among them. And we know 3 power k is a generator if and only if k, phi of 17 is equal to 1. If and only if k, phi of 17 is 16 with 1. So what are those? So now find out all those k's which are relatively prime to 16. So k is 1, 3, 5, 7, 9, 11, 13, 15. And suppose k is equal to 2, you take the GCD of 2 and 16 is not 1, it is 2. Therefore 2 is not there, 4 is not there, and etc. etc. The remaining things are not there. So K belongs to these 8 numbers. So what are the generators? 3, 3 cube, 3 power 5, 3 power 7, 3 power 9, 3 power 11, 3 power 13, 3 power 15 are all the generators of U17. They are 8 in number. Agreed? Agreed. Now let's get into the statement given in option 2. If A is a primitive root modulo 17, then A square is not necessarily a primitive root modulo 17. Now we take A is equal to 3 is a primitive root modulo 17, but it's a square. A square is equal to 3 square is not there in the set of the generators of U17. 3 square is not there in this. Therefore, A square is equal to 3 square is not a primitive root modulo 17. And these, what are these generators? They are primitive roots modulo 17. Agreed. That means A square is equal to 3 square is not a primitive root. Therefore, the statement that is given in 2 is true, is not necessarily true. Yes, it is not necessarily true. Thus, the option 2 is true. Now, we move on to the other options, and we have, these are all the generators, and these are all the, primitive roots modulo 17. Take the option 3. If A comma B are primitive roots modulo 17, then the product AB is a primitive root modulo 17. We take A is equal to 3, which is a primitive root, and B is equal to 3 cube, which is a primitive root modulo 17. But its product AB is 3 into 3 cube, that is 3 to the power of 4, which is not there in this. Therefore, it's not a primitive root modulo 17. Therefore, option 3 is not true. This is not true. This is option 3. Option 3 is not true. The fourth option is product of primitive roots modulo 17 between 1 and 16 is congruent to 1 mod 17. The product of primitive roots is 3 into 3 cube into 3 to the power of 5 into 3 to the power of 7 into 3 to the power of 9 into 3 to the power of 11 into 3 to the power of 13 into 3 to the power of 15, and that will be 3 power 64. 3 power 64 is congruent to 1 mod 17. Why? Because 3 power 16 is congruent to 1 mod 17. Why? Because 3 is congruent to because 3 is a primitive root modulo 17. Because 3 power 16 is congruent to 1 mod 17, 3 to the power of 64 is congruent to 1 mod 17. Therefore, the product of the roots of modulo 17, primitive roots modulo 17, is congruent to 1 mod 17. Therefore, option 4 is true. And in the above, this is the option 3 is not true. That's what is not true, 3. So, what is the answer to this question? The answer to this question is option 2 in the previous slide is true, and option 4 is true. Option 3, option 3 is not true. Option 2, which is there in the last slide, is true. So that is the detailed discussion of the solution of the problem, which is based on the concepts of primitive roots modulo 17 from number theory. And I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.